Hi, in this tutorial I'm going to talk about the likelihood function. The concept, what does likelihood function mean? Then I'm gonna talk about the maximum likelihood estimation. How do we do that? And I will apply the algorithm on two well-known distribution, Binomial and Gaussian. To see how can we derive the parameters for these two distribution to estimate the maximum likelihood. Okay, let us start with the concept of likelihood function. Imagine you have a fair dice, and you throw the fair dice, and you're expecting to get one of these numbers with a chance of 1/6. So actually in this case you have the parameter, which is the mean, and you're interested in outcome. I mean, in a probability, usually that's the case, that you have the model and you're looking for outcomes. For instance, you're interested to know what is the probability of number on a dice less than 3 or 4. Or when you throw a fair coin, you know that the it's a fair coin, so the chance of head and tail is 50%. And you're, for instance, interested to know what is the probability of having 3 tails over 10 trials. So we in these cases we had the parameters which is a mean, and we were looking for the outcome probability, but in the likelihood we have the observations, and we are looking for a model, the parameters, the mu, for instance. What was the mu that has given us such a observations? For instance, you throw a coin and you see you're getting more tails than heads, so you became suspicious it's not a fair coin, and you like to know the probability of head and tails. You know that it's not 50-50%, so what is the probability of head and what is the probability of tails according to this observation? Okay, we also know that if A and B are conditionally independent of event C, means the joint probability of A and B is equal to probability of A given C multiplied by probability of B given C. This is something obvious, we know, conditional independency. Okay. Okay, let's review the steps that we do to find the maximum likelihood. Okay, we assume that our observations are IID, means they are independent and identically distributed, and that basically that means we have, okay, x1, x2, xn, we have n observation, and they are IID, so the probability, the joint probability of them is according to this equation, probability of x1 and x2 and x10 given eta, which is our parameters here, is equal to the joint probability, the multiplication probability of x1 p of x2 eta p of xn, which we noted like this. Okay, so the general steps for maximum likelihood estimation is we use this property. I mean, we assume that our data, our observation, or IAD, and it makes sense. For instance, if you throw a dice, the result on the second time nothing to do with the first time. They are not dependent on each other. So what do? We first use this. So we use our PDF or PMF function if it's dependent on if it's continuous or discrete, and then we use the logarithm ln function to turn this multiplication to a summation. So we use log to turn this to this, because it's much easier to work with the summation. And the reason is we know that the ln function will form like this, and we know that it's monotonic and increasing. Means if x1 is less than x2, then the ln of x1 is x2. So, oh, sorry, ln. So actually, if you find the maximum parameter for the ln function, it means we have find the maximum parameter for our function. So this is only for make the life easier. And then we do some simplification, and that means we try to eliminate the things that we see in our formula that nothing to do with the maximization, and make it simple. And then in the last step we compute the derivative according to our param, and we equal it to 0. And you know, it's a high school math that when you have a function and you want to find the extreme, the extremes are happening at the point that the first derivative is equal to 0. So these are the steps that we take to find the maximum likelihood. And now I'm gonna do it for, as I said, two famous distribution, binomial and then Gaussian. Okay, let us start with a binomial. So we know that the PMF for the probability mass function for a binomial distribution is like this, that okay, you throw a coin and let's say f of y, and you know the chance of winning is p, the chance of losing is 1 minus p, and you like to know the chance of winning y times. So the chance of winning, so you have to win y times, and obviously you have to lose n minus 1 times. We have done it n times, and we like to know the chance of winning n times in this y time. And you could have a different combination of winning, losing, winning, winning, losing, winning, winning. So we have to take into account also the these combinations. So we also have this guy here as well. Okay, so now let's write down the likelihood for the p. So as you can see, we are looking for the we are looking for the P. We're interested to know what was the model, what was the probability of head or tail that gave us this. We have an observation, and we like to know know more about the coin, that was a fair coin or it was biased on one side. So as I said, we use the IID property here, and this will give us this. And when we multiply them, basically here in the power, we just do the summation, because it's obvious from the. And it's the same for the complement probability, so that's going to be 1 minus b, and n times n. Okay, now we do the second step. We compute the ln of this function. So actually we are looking for the p that maximize these. Okay. B n times n. So just to make it clear, the small the capital M is the number of times that we have done it, and the small n is the number of observation. Okay. So if we take a ln from this, we're gonna have all this multiplication gonna turn into summation. So we're gonna have sigma I over n ln of so the variable here is p. So this is constant. So this is like a coefficient for this plus the power gonna be gonna be here. Multiple and maybe I'll just write it big one here. Okay, so we have this term. Now we compute the derivative. And as I said, we are looking for the p that maximizes value. So our variable is p, and we equal it to 0 to find the extreme point. So this term is nothing to do with the p, so the derivative is 0. And from this guy, this is a coefficient, so it's gonna remain, and it's gonna be 1 over p. So we're gonna have equal to over p. And it's the same, so it's going to be 1 minus p okay. Now we just okay, sorry, I made a mistake here. It's minus because of the polar, so it's minus here. Okay, now if I take this guy to the other side and do some multiplication and simplification, I will have 1 minus p sigma I over which consequently will, you can see I can just cancel this guy with this term, so the p gonna be okay. So this is the p that will maximize the likelihood for a binomial distribution. Now I'm gonna do it for case of 1D Gaussian. Okay, so we're looking for the parameter, which in this case is mean, that let me just write it down. And you know the covariance is when you have the mean, you have also the covariance, because you have to observe data and you only need the mean. So I use the IID property here. So it's gonna be V I mean here it's likelihood function. We are looking for the mean. That IID property gives us 1 to n. And then we plot the PDF function of the Gaussian distribution. We know the p, so we just plug it in, and we're gonna have okay. Now we compute the ln, the logarithm, which turn this multiplication to summation. So we have oh, sorry, I had written down the sigma. Here, xi minus mu over 2 sigma 2. Okay, which is, and as you can see here, we have a positive number, and negative number. So if you want to maximize it, then it's equal to, it means this term should be 0, because here we have always positive and then multiplied by a negative value, which give us always negative. So and we could just solve the we just could compute the the derivative and equal it to 0. But I mean, we can obviously see that this is equal to minimization of this problem. This is a fixed value, so we can just cancel it out. But we could obviously see that we should minimize this guy, which means if I just take out this mu, so it's a constant, sorry, it's gonna be n times mu, and I move it to the other side, so I get rid of this minus, and I will have, which means mu is equal multiplied by 1 over n. Okay, so that's it. This is the way that you compute the likelihood for your distribution. I mean, if it's more than 1D, then instead of this variance, you have covariance, and the mu is a vector. So when you here compute this, it's gonna be a vector. But the idea is still the same. So using IID property, then use a logarithm, cast the multiplication to the summation, and then compute the first derivative, make it equal to 0 to find the extreme point, and then solve it. Thank you for your attention.